NASA scientists are one step closer to unlocking the secrets of the universe. The James Webb Space Telescope completed its final deployment sequence.
At first, it looked routine. A distant galaxy, faint, ancient, exactly the kind James Webb was designed to study. The image resolved slowly on the monitors. Infrared light stretched across billions of years of cosmic expansion. Another data set from the early universe. Nothing dramatic, no sudden spike, no system alert, no headline moment, just numbers coming in. But then, something happened that you would never notice unless you were trained to look for it. The conversation stopped. One of the scientists leaned closer to the screen. Another opened a secondary analysis window. No one said anything for a few seconds. Then, someone quietly asked, "Can you rerun that?" Within minutes, more people were in the room. Not because of excitement, because of uncertainty. Phones came out, simulations were pulled up, previous deep field comparisons were opened side by side. And that's when NASA realized James Webb hadn't just found another distant galaxy, it had found something inside it. Something that shouldn't have been there, at least not yet. And the reaction wasn't celebration. And the reason that moment mattered has nothing to do with danger. It has everything to do with timing. The galaxy Webb was observing wasn't nearby. It wasn't a mature spiral like the Milky Way. It existed less than 600 million years after the Big Bang. That's not just early, that's cosmic infancy. At that stage in the universe, galaxies were still assembling. Gas clouds were collapsing for the first time. Heavy elements were rare. Structure was chaotic. Webb was meant to study that era, to understand how the first galaxies formed. But as the data pipeline finished processing, the inner region of this particular galaxy refused to look simple. Brightness was concentrated in a way that didn't match normal star formation patterns. The central region showed energy output that was steady, not explosive, sustained, ordered, deliberate. That's when the modeling began. In astrophysics, you don't jump to conclusions, you eliminate possibilities. First question, could this be an intense burst of star formation? Early galaxies are messy. They produce massive stars rapidly. Those stars emit huge amounts of radiation, but starbursts leave fingerprints, irregular structure, patchy distribution, short-lived variability. This signal didn't behave that way, so they tested dust models. Could interstellar dust be distorting the spectrum? Infrared observations are sensitive to that. The correction didn't remove the anomaly. If anything, it clarified it. Then came the velocity mapping. When light is stretched or compressed, it tells you how fast material is moving. The inner gas wasn't random. It showed organized motion around a central point. That narrowed the options dramatically. But no one in the room said the obvious word yet, not until the mass calculations were quietly run. Here's the part that changed the tone. When you estimate the gravitational influence required to produce that kind of motion, you get a number. And that number has to fit inside the timeline of the universe. The galaxy they were looking at existed when the universe was less than 5% of its current age. There hasn't been much time for anything to grow that large, and yet the central object implied by the data was not small. It wasn't stellar scale, it wasn't borderline. It was already well into the range that astrophysicists associate with actively feeding black holes. Not the billions of solar mass monsters we see later in cosmic history, but far too massive for its age. That's when the reaction began. Not shock, not excitement, adjustment. Because black holes don't just appear fully formed, they grow. Typically, they start as the remnants of massive stars, a few dozen times the mass of our sun. From there, they accrete matter. Gas falls inward, radiation escapes outward, mass slowly increases. But there's a limit. It's called the Eddington limit. If a black hole feeds too aggressively, the radiation pushing outward counteracts gravity pulling inward. There's a natural speed limit on growth. And if this object followed that limit from the moment it formed, it shouldn't be as massive as Webb's data implied. Not in that amount of time. So either it formed from a much larger seed, or it grew faster than we think possible, or our early universe models are missing something fundamental. None of those options are trivial, because supermassive black holes are not side characters in cosmic evolution. They shape galaxies. They regulate star formation. They influence structure on enormous scales. If they formed earlier and grew faster than expected, then galaxy formation timelines shift too. That's why the room got quiet. Because Webb didn't just detect a black hole, it detected one that challenges growth assumptions. There is a theory that could explain it. Instead of forming from dead stars, some early black holes may have formed directly from collapsing gas clouds. No supernova, no intermediate stage, just massive primordial clouds collapsing straight into black hole seeds thousands of times the mass of the Sun. That's called the direct collapse model. It's been debated for years. Webb's data doesn't prove it, but it makes it more plausible. Because if the seeds started larger, the timeline problem shrinks. Growth doesn't have to be extreme, it just has to be steady. James Webb sees deeper into the universe than any telescope before it because it observes an infrared light. As the universe expands, light from distant objects stretches. Ultraviolet and visible light emitted billions of years ago arrives here as infrared. Older telescopes couldn't see that era clearly. Webb can. And what it's revealing is that the early universe may have been more efficient at building massive structures than our simulations predicted. That doesn't mean cosmology is broken, it means it's being refined. This is how science moves. Observation first, adjustment second, understanding third. Minutes after NASA realized what James Webb had found, the reaction wasn't dramatic, it was disciplined. New simulations were started, alternative scenarios were tested, independent teams began checking the numbers. Because if this observation holds, and if more like it appear, then the timeline for black hole formation shifts earlier. And when black holes shift earlier, galaxies shift earlier. And when galaxies shift earlier, the structure of the universe evolves differently than expected. That's not a small correction. That's a recalibration of cosmic history. James Webb wasn't built to confirm what we already believed. It was built to test it, to push our models into regimes they hadn't been tested before. And sometimes that push reveals something subtle. Not an explosion, not a crisis, just a number that doesn't fit neatly. A growth curve that bends slightly too soon. A structure that matured faster than expected. And in those moments, the quiet recalculations, the model comparisons, the careful reanalysis, that's when science is at its most powerful. Because the universe isn't obligated to match our expectations. And James Webb is showing us that the first billion years after the Big Bang may have been more extreme than we imagined. Not chaotic in a dramatic sense, but efficient. Relentlessly efficient at building gravity wells where they weren't supposed to be yet. And that's why, minutes after NASA realized what Webb had found, the reaction wasn't celebration, it was respect. Because the early universe just got more complicated. And that means we still have more to learn.